Welcome to tonight's San Francisco Bay Area ACM talk. The title will be Secure and Interpretable AI, Scalable, Interactive, and Practical Tools. The speaker is Dr. Polo Chau, Associate Professor of Computing at Georgia Tech. So about the San Francisco Bay Area ACM, we're a local professional society of the ACM local chapter, founded in 1957. Our objective is to promote the knowledge of modern computing. We want to create community, support networking and hiring. We have only a $20 annual membership for our chapter. We don't get any financial sponsorship from our headquarters of the Association of Computing Machinery. You can see our upcoming talks on our meetup site, SF Bay ACM, and about 180 past talks on our YouTube channel. We generally have 2 monthly meetings or seminars like this. General computing one is usually about the 3rd Wednesday of the month, and the data science SIG is typically the 4th Monday of the month. We also do various meetings with other IEEE societies or valleyml.ai. Here's some of the upcoming events. Right now we have a large group of data science SIG events coming up. So next month on September 11th and 12th, on Saturday and Sunday, we have a professional development seminar or PDS. It's a 6-hour class. It's 10 in the morning till 1 p.m. on the 2 days of the weekend. It's natural language processing with PyTorch by Ravi Alango, a senior data scientist at a stealth startup, and Yashesh Shroff, PhD, a lead AI ecosystem GPU planner at Intel Corp. So here's the web link for that. The cost is $125. It's one of our fundraisers for the year. And you can use promotion code SFBayACM20 for a $20 discount. So we very much invite you to use the ACM discount, even if you just heard it on the meetup site. Because there's other channels promoting it, and we like to track the ones that heard it through our events. Then for our September data science talk, we have another speaker that's battling for deep fake dystopia. Dr. Demir is a research scientist at Intel Corp. So that's a 7 p.m. talk like this one. And then I just now have been working on this pair of talks. There's a Monday night talk and a Saturday 6-hour PDS class on the same topic, an open Apache architecture for a 1-second SQL query on a petabyte plus of data. So that's with Dave Nielsen of Dremio. So this will be using a wide variety of Apache tools for this, open source Apache tools. So you can come for the evening talk in October, and then following that, on a following Saturday, then we'll have a 6-hour class. That's a hands-on class. So we don't have any web links for this. We're still working out some of the details for this, but look for this to be posted on the meetup page coming up. So you can use chat in the Zoom if you have questions for the speaker. So I can read any questions to the speaker. I'll be the moderator. I'm Greg Murkowski. Let's see. Also, if you have any job postings, then you can also post that in the chat. Like if you have a link or some kind of description for people to see the details. You know, don't do pages and pages of job description, but just enough to point people where to look at. If your company's hiring a data scientist, you know, this is a data scientist focused SIG. So if it's something unrelated to data science or big data or math, then it wouldn't be something to post here. If you do have questions, try and have it a moderate length, not super long, just to make it easier for the speaker to answer. So now to introduce tonight's talk, Secure Interpretable AI, Scalable and Interactive and Practical Tools. So about the talk, research shows that AI and ML models are often vulnerable to attacks. Predictions can be difficult to understand. So they're gonna present a first attack, which was from ShapeShifter, that fools object detectors, and talking about a fast defense that counters an inactive system to study. They've got a scalable interactive visualizations that provided key leaps for model interpretability, explorability, and increased usability. The latest work, Summit, is an interactive system that summarizes and visualizes. About our speaker, he's a professor, associate professor of computing at Georgia Tech. He co-directs the Masters of Analytics program. He's a director of industrial relationships at the Institute of Data Engineering and Science, IDEAS. He got his PhD in machine learning from Carnegie Mellon, and he won a computer science dissertation award, honorable mention. He's gotten grants from National Science Foundation, NIH, NASA, DARPA, Intel, Google, and a much longer biography that you can see in the meetup site. So please help me have a warm welcome for Dr. Chau. So I'll turn it over to you. And if you have any other introductions you'd like to do, please go ahead.
Okay, thank you very much for the introduction, Greg, and for invitation for me and also everyone in the audience for attending the talk. So I'm dialing in from Atlanta. So it is 10 p.m. for us, and also today is our first day of class, actually. So this it's been an interesting day. So hope all of you are doing great. So as Greg mentioned, so our topic today is about secure interpretable AI. And I'd first like to thank ACM. So I'm giving this talk as ACM distinguished speaker. So thank you for the ACM for doing that, and also Greg's invitation. So today's topic, I'd like to give some highlights about latest work that we have been working on around secure and interpretable AI. And so this is the two major research thrust that my research group at Eurotech has been working on. So at Eurotech, we say we're working at the intersection of AI, artificial intelligence, and human intelligence. So more technically, we actually have been working in the intersection of machine learning, data mining, visualization, human computer action. So there's all these names, all these buzzwords. So it's just, especially these days, everything say AI. So what does it mean? So it really means that we are trying to make and create scalable interactive tools to help people make sense of a large amount of data and model. So I always like to start my talk by thanking my students because everything that you see today is work that they did. So my PhD student from the top left, and then my master's student and undergraduate students, and also our recent alum from our group. And so you may ask, like, why are we focusing on these two? Why secure AI and interpretable AI, and also why do our group focus on them, and why are we talking about these today? And so there's actually a lot of close connection between them. And for the secure AI part, probably quite a bit easier to grasp because you probably are already seen a lot of these from popular news. So now AI or machine learning is used a lot in almost everything. Right? In a lot of times, it's more safety critical application, like self-driving car, for example. And if you're not careful, people can die. And you may say, well, so that's only for these scenarios that maybe you need to worry about that, but actually not really, because now AI or machine learning is pretty much used everywhere. So it's only a few years ago that it was actually used to be a joke. It's like, well, you have this toaster that is hacked, and maybe say, why would you even have a toaster that would have a chip in it? Well, actually, it does. So now you have a smart toaster. Actually, pretty much you can have anything that is smart. Right? So the light bulb is smart, your alarm clock is smart, everything is smart. So what that means is that it's no longer just something that you will say is a special cases. It's actually only going to be more and more devices that you need to worry about. And so what is the problem with that? So when we're studying secure AI, we're trying to develop AI that was secure, maybe more robust against attack, or sometimes it's a natural harm. So people work on both attacks and defense. And a dirty secret, however, is that even for experts working in this field, if you ask them, you can just ask them the question. So your AI seems to be working very well. So why is it working so well? If we ask them the why question, then they usually would not know the answer. Actually, there's so many techniques out there that are now so complex. If you ask that question, how does it work? Like, why is it that give your technique such an edge over other technique? Or you would say you have a really good defense technique, like a technique that's robust to attack, or like maybe it worked really well for self-driving cars. So why does it work? If you ask the question, often people actually don't know. Experts don't know. And the reason is that a lot of these models are so complex that these days, often people just willingly say, well, we don't really know what is going on, so let's just use them as black boxes. And of course, we know there's a problem with that. So if a black box is, then when it breaks, we don't know how to handle it, how to fix it. So what we would like to do is use techniques that are more interpretable. Here, we're not really trying to show all the details, like every single thing. So that is probably overwhelming. So rather, we want to help the user figure out what's relevant, what's important to look at. And our approach is to use scalable interactive user interfaces. Often it's interactive visualization to help the user understand these large, complex machine learning models. So there's a connection there. So secure AI and interpretable AI. So we would like the interpretation, the visualization to help us understand what these attacks and defenses are doing, with the hope that we will create better, more robust machine learning models and AI models. So for today, I'm going to give you an overview of some of our latest work. So in both areas, and some are at the intersection of them. We'll start with secure AI. We'll talk about ShapeShifter, that first technique that we're full object detector. And the reason we study attack is so that we can create better defenses. So of course, I will also show you some examples. One's called Shield and Adagio. So they real-time defenses you can run in real time and in high frame rate for both image and audio. And after that, I'll also show some of our latest work where, based on a research study, looking at attack defense, and we look at some of the gaps currently in the research landscape, which is a lack of large data sets and also toolboxes for people to use to further research. And after that, then I'll move to the second part of the talk, where we look at some of the latest tools and systems that help people interpret what these models are doing. For example, Summit and Bluff, so they are a collection of techniques, scalable ways to understand what's happening in deep neural networks, or DNNs for short. And after that, then I'll end the talk with 2 surveys to point you to some directions if you're interested in a topic to learn more about visual analytics in deep learning, or what are the latest status in the area of interpretable AI. Okay, so I'm going to start with secure AI, particularly ShapeShifter, the first technique that's for object detector. So this was developed joint work with Intel. First author, Shanji Chen, so he's now an assistant professor at National Taiwan University. And so what is ShapeShifter doing? Like, why do we study attack on object detector? So you might probably have heard a lot about image classification, and that's very different from object detection. So for image classification, often you'll say this is a task that's arguably a little bit simpler. So what that means is that you're giving an image, you just classify it into one of the labels. For example, here this image, you might say this is the class is car, right? So there's a single label. However, if you really zoom out from the image, for example, or maybe in a real context, often you might see that an image contains not only a single thing, it may be multiple things. There might be people in it, there may be something in the background, buzz in the building, or multiple people, and so on. So what that means is often in the real world, we not just want to give a class, we actually want to find out what are the objects in an image, localize them, and recognize what they are doing. Right. So that's a major distinction between object detection and image classifier. So ShapeShifter is a technique that attacks these object detection methods. So you know about image classifier, and you probably also likely have heard that deep neural network-based image classifier are pretty vulnerable. So you probably have seen this before many times, sometimes panda image, sometimes stop sign. What it's saying that if you have an image of the stop sign, let's say, you can write an algorithm that would change the pixels in a way that human beings cannot really discern if there are any difference. So the correct label would be a stop sign, but you can change the pixel in a way that people cannot determine. Well, then now the image classifier would say that it's a max limit speed limit sign. So, however, often there's assumption. So why can we do that? Right. So assumption is that we assume the bad guy, whoever create these pixel manipulation, they have access pretty much to everything that they want. They have access to data, they have access to the model, the neural network model, which is why they know what not to change. However, we call these threat model are not very practical, particularly in the context of, let's say, self-driving car. So let's say you're driving a self-driving car and you use object detection to figure out what's on the road. So when your camera is pointing at the road, there are actually quite a few things going on. Right? You have your camera, your video camera from your car, or multiple sometimes. They will capture what is surrounding the car, and then they will do quite a bit of processing. right within the car. They have the GPU, graphics card, and so on. And then after that, they do the recognition. So there's maybe a stop sign, there's maybe a tree, there's a person in it. So if we're used, often the threat model that academics are using, where the bad guy would have access to pretty much anything, right? Access to the model, access to the whole pipeline from capture to process to recognition. So what that really means that they are launching what we call a digital attack. So they can manipulate the images, manipulate the whole pipeline, manipulate the model parameters and everything. So that kind of begs the question. So if the attacker really have all these access to the whole pipeline, so why do they bother to manipulate the model? Why don't they just crash a car? Right? So which is why we say, well, maybe that's overly making the attacker overly powerful, right? Because if the attacker is really that powerful, can hack into the machine, hack into the car, then they probably don't need to do all these attacks. So what we think is more likely is going to happen is what we call a physically realizable attack. So what that means is the bad guy in this case, they don't need to hack in the car. All they need to do is to manipulate the physical environment. For example, they may put something on a stop sign, right? And then in a way that maybe people cannot see it, then that's it, then they crash the car. So do we call this physically realizable attack? No need to hide in the car. And what we think is more realistic, and also we can launch target attack and under target attack. So what does that mean? So I'll show you a very quick example of what ShapeShifter can do. So here's a video. On the left-hand side, so that's the real stop sign. On the right-hand side, here you will see a little bit fishy going on. That's a stop sign that's generated using the ShapeShifter technique. So this is a video. So we want to fool the object detector into mislabeling the stop sign as a person. So here I'll play the video. We're actually having Chau, first author, actually driving his car towards the two stop signs. So as you drive closer, you'll see that the correct stop sign correctly labeled. The fake one, from a distance, actually it's not detected at all, and only when it's getting closer and closer, then now the object detector says, oh, well, there's a lot of people, person, right? So that is what ShapeShifter can do. And then in a later example, you'll see that we can actually change the detection to anything you want. It doesn't need to be people. It can be like a board, it can be like making it disappear, anything. So we may say, well, okay, so why is it so hard? So I'm pretty sure I've seen some attacks like this. Yes, you may. So you may have seen this physical attack happening for image classifier, but you have not seen attack on object detector until ShapeShifter was developed. So these are examples of image classifier. So you can put on eyeglasses, you can have something on a turtle, or have some stickers on stop sign, and these can fool object detector. I'm sorry, image classifier, but not object detector. Actually, initially, people have thought that, well, if you try to attack an object detector using a physically realizable attack that's designed for image classifier, it turned out that it did not work. So here we're showing you that for object detector, it has no problem in correctly labeling the object. Right? And actually, for a while, people say, well, object detector is hard to attack, so maybe we are good, so we don't need to worry about it. But actually, no. So now that we know, in hindsight, particularly, that you can attack object detector, and it turned out to be not that difficult. So particularly in ShapeShifter, we are attacking a state-of-the-art object detector called adversarial. So to explain why it works and why the attack works, I'll briefly give you an overview of how the adversarial model works. It's based on what we call a two-stage detection. So first stage of the object detector is actually try to figure out what are the potential regions in an image. Let's say you have a camera in your car, right, pointing towards a road in front of you, and then try to scan. Okay, so there is there likely to be an object here? Is it likely to be an object here? So these, what they call is region proposals, and some of these regions can overlap. And then for the regions that may be overlapping, then if you go to stage 2, you try to say, oh, so for this region, what is it? So maybe it's a car, maybe it's a stop sign, maybe it's something else. So it's a two-stage approach. What that means is that if you want to fool, let's say, this object detector, you kind of need to fool all these regions. You cannot just fool one region. So you have an illustration showing you that, let's say we have 3 overlapping regions potentially that may contain things. right? So you cannot just fool one because the other two would still give the correct label. So you need to fool all three of them. In practice, actually, even can be more than three. So that means now you kind of need to fool like an ensemble of method. And then secondly, we also need to worry about distances, angles and lighting, and all these physical elements that we need to worry about, because now we're not just looking at the image at one angle. We actually could be driving towards it. It could be from an angle. That could be light reflections and everything, right? So for these two reasons, make the attack. At least originally we thought, well, actually that's pretty tricky. So how do we tackle this? So it turned out that we can tackle them one by one. The first is that, well, if you say you need to fool the ensemble, well, then one way is that we really design our minimization or optimization to be to minimize the sum of classification noise. So that means we attack all of the regions at the same time. And also we take advantage of the fact that for darker color, let's say for red, we can actually change a lot more, change the pixel a lot more, because human beings are not as sensitive to changes in a darker color. So that means you can change a lot more in the pixel for the red area. And to tackle the second issue, the robust, the physical element, so what we do is we adapt expectation over transformation technique, originally designed for image classifier, but now for object detection. So in a nutshell, what it's doing is that means when we come up with a pattern, let's say ShapeShifter come up with a pattern, we actually also rotate it, we scaled it, we apply a different background and lighting, so that the attack would get used to seeing these different background, this variation, and would still work. Right? So using this high-level approach, you can actually come up with anything you want. You can fool the object detector is mislabeling things as person in just sports ball, or untargeted, meaning they get disappeared. So I'll show you another example where in this case this is untargeted attack. So again, driving closer to do stop sign, the correct one, benign one on the left, and then the adversarial one on the right. In this case, you may find it's even a little bit harder to see. So for many frames, most of the frames that it was not detected at all. It's only when you get really close and something fishy is going on, and maybe a few frames that's labeled as bird, and then that's it. So pretty much disappearing. So when we first developed it, we found this is pretty scary, and I think it still is pretty scary. And hopefully we don't see this in the physical world anytime soon. But there is enough interest that DARPA now has a program called GUARD, guaranteeing AI robustness against deception, which Jpeg is also one of the performer with Intel. This DARPA program highlights ShapeShifter attack as a state-of-the-art physical attack, and is also one of the techniques attack that we actually want to build defenses against. The whole GUARD program is about how to develop defenses to protect AI from harm, and ShapeShifter was one of the techniques they want to counter. So you may ask, okay, so great, so we have ShapeShifter, so now we know it can be scary, so that there's some attacks. So why do we study this? So attack is not really our ultimate goal. So studying attack is so that we know how the bad guy thinks, and so that eventually we can create better defenses. So shield is a defense, which is in part motivated by our observation on working on attacks. Particularly, we saw that there's a gap in a lot of defense techniques that people have come up with. So again, this is a joint work with Intel, and our focus here is how do we come up with defense that is fast to run, is practical. In this case, we're dealing with digital attack for image classification. So a particular gap that we want to fill is that we want to make sure a defense does not just look good on paper. So we look at the research landscape for adversarial machine learning research. So that means attack and defense for machine learning. So quite a lot of work is on attack. If anyone worked on security before, you will know that academia publishing an attack paper relatively easier than defenses, because if you're an attacker, you only break the system once and then you're good. You want to be the good guy. Oh, okay. So now you need to kind of defend against all the attack, because a reviewer could easily say, oh, well, okay, nice defense. Does it work for this attack? Well, it may not. Right. So if you look at defenses, well, then there's even fewer techniques that are what we call fast and practical. So that means, let's say, running in high frame rate is something that you can use right now, today, rather than writing for like 2 or 3 years and to tech transfer and everything. So our shield defense is to fill in this important gap, which is we want to come up with fast and practical defense. So what is it doing? So actually the idea is very simple. So it's countering image perturbation for image classifier. So particularly we're using compression as the mechanism for defense. So I can explain everything in one slide, this single slide. So here I'm using an example, let's say an image of a dog, Labrador Retriever, and now the attacker can manipulate the image pixel. So again, in ways that people cannot tell. So that if you pass it to an image classifier, now it would fold the image classifier and would label it as chainmail. Actually, you can change it to anything you want. You can change it to a person, you can change your car, whatever you want. So we are aware of these techniques, and then we ask ourselves a question, okay, so a lot of these techniques claim that they're adding this noise or in some way this high frequency noise perturbation that our human eyes are not very good at picking up. So then why don't we just come up with a defense that is specifically designed to remove or to counter these high frequency perturbation? So that was the main idea. And it was how we look at, well, are there techniques out there that we can use? And turn out, yes, there is actually Jpeg compression that has been around for a very long time. So you use the internet every day. So that means you're actually using the result of compression, Jpeg compression every day. Whenever there's a large image, but particularly natural images transmitted over the web, it's mostly likely compressed using Jpeg compression. And the reason that it works, that can reduce the image size so much, is exactly because it removes things that human beings, our eyes cannot see. So then we say, okay, why don't we use it? But use it systematically to remove these high frequency perturbation. So that's exactly the idea. So that means now whenever you have an image, I don't know whether it's manipulated or not, and I don't really care. So I just compress it. So that for the manipulated one, it will become correctly classified after compression. And for the one that are benign, no change, hopefully. So it's go well. So that's our main idea. And of course, there's a little more detail. So particularly when we apply compression, we probably don't want to compress the image using the same compression level all the time, right? Because if we do it, then the attacker then, oh, okay, we know that you're always using this compression level. We just design our algorithm like that, attack like that. So rather we use randomization. So specifically, we divide up the image into blocks. And then for each block of the image, we compress it using different level. So it could be lower compression, high compression, and a random way. And we call stochastic local quantization, very fancy way, but it's just to say that it's divide the image in a block, compress each block using different compression. There's a little bit more details in it, not only the random compression, but also we do something model vaccination. Also, this is before pandemic. So at that time we do vaccination, we mean is that we try to retrain the model with more JPEG compressed images so that I would get used to seeing these JPEG compression artifacts. So if you ever zoom into a JPEG compressed image, you will notice that there are actually quite a bit of an artifact. So we want the model to get used to seeing this so that it's more robust against these compression artifacts. And also we not use just one model, we use multiple. A similar idea as using like randomization. So we want to have multiple layer defenses. So I use the ensemble. So all together, then they form the shield defense. So we run it, this is about 2018 or so. So we did a large-scale comparison evaluation against some state-of-the-art techniques at that time. So what we're showing here are two results comparing two tech. One is IFGSM, the other is FGSM. So these are popular tech methods. So horizontal axis is the perturbation strength. So more to the right, that means more manipulation. And the vertical axis here is accuracy. So higher is better, and horizontal axis increase more to the right, stronger attack. So what that means is that what you expect is as we increase the attack strength, the accuracy should drop. So what we are seeing here is, let's say, the dotted line. Dotted line means no defense. So as you see the attack perturbation, as we increase even pretty low, the accuracy already dropped to almost zero. So if you apply the shield defense, which is the orange line, then you can boost and break the accuracy back up to pretty high. And it's higher than, let's say, individually applying the Jpeg compression on a fixed level, let's say 20, 40, 60, 80. So we can actually combine all of them in a random way, as I described, and you can give the shield accuracy, which is really good. So we notice that as we increase perturbation, eventually you can always bring the accuracy down to 0. Yeah, so there's it's not a matter whether we can do it. The question is how much perturbation that we can counter. So that's the main point. So that means the gap is the main thing we want to look at.
A question.
Yes.
Would this be helpful for models that, let's say I'm not doing it just for defense, but just to help increase robustness? Like in the augmentation pipeline,
yes.
where you're already switching right, left, shifting up, down, things like that. Maybe, and you had that 3x3 grid, so where you're doing the different things.
Yes.
So maybe add that, but not in the exact same 3x3 point. Maybe have random location of the horizontal and vertical lines, just so the model doesn't get too fixated on the exact 3x3 grid. But would that help just for general robustness?
Yes. So that's a great question, and the short answer is yes. Actually, during our evaluation, we found that, but just by retraining the model, so now we often call it data augmentation, or sometimes also adversarial training, for example. So this is a pretty broad term, of course. We found that even with benign accuracy would increase, not just help with countering, but even helping benign accuracy. So at the high level, you can think of these retraining with Jpeg artifact and so on is just to let the model to get to see more variation of the data rather than seeing an image just like one version. Now you can see multiple slight variation, which is actually pretty much like how real world works, right? Because we look at something like using we're actually looking at many small variation, but we kind of generalize it. Yeah. So the answer is yes. Thank you.
Okay. A follow-up question, if I may. Sometimes also I'm using 3D augmented, like video game generated data, just to increase the variety and kind of a design of experiment style. But would some of the Jpeg compression just help with usefulness of the 3D image data to supplement the training?
Yeah, it's a great question, and another great question. I think short answer is also yes. So actually now we have some ongoing work. We are looking at 3D models, I think synthetic data, particularly in the context of the GOT program. Yeah, so we are looking at, and yes, I think so. So same idea. So how do we generate more data, more variation, different perspective for the model? So actually, that's quite a lot of work and research right now to kind of ask a question, study that in depth, like how much variation to really look at, how good are some of these like state-of-the-art models are. Even though they have trained on a large amount of data, but is it sufficient? So that I think there's still an unsolved problem. Yeah, but short answer is yes, I think so. Yeah. Okay. Yeah, there we go. So I continue. So as we mentioned, a core reason for using Jpeg compression is that we want it to be fast and practical. We don't want to say, oh, wait, let's wait 5 years. Like 5 years from now, well, that may be better attack. So we want something that we can use right now. No need to wait. And actually, that is something that we got a tech transfer to Intel because of the readiness. So we compare a shield to other techniques, let's say for median filter for removing noise or total variant denoising. Jpeg, because of all the optimization, years of research, and also hardware software acceleration, you can do an orders of magnitude faster than all the other approaches. So that's a really attractive thing. And also compression actually has been a foundational approach, in particular in data mining. So that got us thinking is not really something that's unique to or only suitable for image classification, but also actually we tried it on audio, defending against audio attack too. So particularly we developed a technique called adagio using the same idea, but in this case we also built it into a more interactive work where we allow the user not only look at the static result, but they actually can play with it. They can upload their own audio sample, they can perform attack, and then also pick a defense on it, and then also look at the hear the differences. So I will show you a really quick demo of adagio. So this is how it looked like initially. So you can click a plus sign and then drag your audio clip inside. And here we're doing an audio transcription. So the correct transcription isn't the party also the analysis engagement of Joanna. So here I can pick a tag. So here we're picking Carnegie Warner attack. And I can choose the transcription that I want to change, want the attack to change it to. And here you'll say, okay, we'll change Joanna to Marisa. So again, if you hear the audio, it sounds pretty much like the benign one. And after applying the attack, then I pick a defense. In this case, I pick MP3 compression. So similar to Jpeg, also compression-based technique. And now they remove the perturbation to bring it back to Joanna. So that's an interactive, fun way to try that. So not only looking at things on paper, they also get to try and pair up the attack and defense. And based on our work on compression, we actually try to extend it even further. We say, well, so for compression, so these are looking at kind of signal, like audio signal, vision signal. So what if we generalize this compression idea to the feature level? Like to something more maybe semantic, more high level, rather than looking at individual pixels or audio signal. So that allows us to develop this technique called unmask, which recently published at Big Data 2020, where now we look at the compression as in compressing an image into these individual features that human being may be able to recognize from an image. For example, let's say you have a image of a bicycle here, right, showing on the left-hand side. So we ask the question, so why do human think that this is a bicycle? Like, well, certainly we're probably not looking at the individual pixel of the grass in the background. We're probably looking at high-level things. We call it these robust features, compressed features. Maybe we're looking at the wheels, and we're looking at the handlebar, and then together, then we say, oh, this is probably a bike because there are these different parts that I detect. However, this may not be actually how a lot of the image classifier are working. So they probably still operating at the pixel level. Okay, so what we think is that, well, can we use this kind of human common sense in some sense, like this knowledge as a defense? So what that means is now, if I have image, can I try to identify where are these parts? And based on the absence or presence of these parts, then we determine whether an image or the classification result is under attack or not. So let's say here we're showing you an image of a bike, and the attack technique change the pixels, again, change the pixel value, so that the model will say this is a bird. So now we're using a mask technique. We try to extract from the image. Do we extract bird parts? Or if not, what do we detect? So in this case, we extract a lot of the bike part. So we compare basically the set of bike features with the set of bird features, and then we see if they overlap. But in this case, we know that they don't overlap because we can see that, well, okay, there's no bird parts. All we see is bike parts. So then we say, well, probably is under attack because you say it's a bird, but I detect 0 bird parts. And even better is that now we can ask the question, okay, well, if you do not detect bird parts, then what do you detect? Well, we detect bike parts. That probably is a bike. So that helps with the rectification. So that's one of our latest work to try to generalize these features to try to correlate the semantic meaning with the image. So rather than just interpreting these pixels at their raw values. So when we're looking at working on these data, including unmasked data, one thing that came up pretty quickly was about the shortage of data. So there's already quite a lot of data these days. There's the ImageNet data, there's other data set that has been released, but we still find that there's a huge shortage, particularly shortage of data that is, let's say, imbalanced, have many classes, many variation, diversity. For example, you can look at ImageNet data, you will say, wow, there's 1 million images, 1,000 classes. It seems to be big, but then we really look at individual classes. So first of all, some of them are mislabeled. And then the other thing is that they're actually fully balanced. So in the real world, that's not really the case. So a lot of things are unbalanced. a lot more diverse than that. So they got thinking, well, maybe there still need more data set. We should probably work on it so to help advance research. So particularly since we have been working on cybersecurity for a long time, we think, well, maybe a good way to do that actually is start with some cybersecurity data sets. So particularly very recently, which was published in New York 2021, just got acceptance, is going to appear later this year. So we developed this data set called MailNet. So this is the largest cybersecurity database in the image representation and graph representation. So what that is published is the graph representation. So what that means is that we have over 1.2 million Android malware, and for each piece of malware, we will represent its function call graph, like which function calling which one as a network. Like nukes are function, edges are the function call, like which function call which one. And on the right-hand side here, you'll see that for MailNet, it is over 100 times larger than whatever is available currently publicly. And also there are a lot bigger graphs and also a lot more classes. So I'm really excited that this could be a data set that help advance both the machine learning research and also the security research. And in parallel, we also have the image version. So this is a work in progress right now. For each piece of malware, we also represent the malware as an image, so that we can also use image-based technique to help with malware detection. Excuse me. So besides data, when we're working on data, we also found that another gap currently is that not only about data, but also about tools. So we are also pretty blessed these days with quite a few libraries, but at the same time, also for a lot of the state-of-the-art techniques, they are still pretty much stay in the research area. So a lot of them are not readily usable. So that also motivates us to develop the Tiger GPU accelerated Python library. So one of the first that has a large collection of techniques that can quantify vulnerabilities, that can simulate these attacks, and also to try different defenses. So they're also really excited about this. Recently, we just got published at CIKN 2021, and also now as part of the NVIDIA Data Science Teaching Kit. So far, I covered some of the latest work in the secure AI side. So we talk about some attacks, some of the defenses, and also some of the latest releases of data and also toolboxes. So as I mentioned, so if you ask people, so how do these defense work? And they say, I probably don't know. So that's so very complex. So that motivates us to look at interpretable approaches. So the second part of the talk, I'm going to show you some example how we can try to interpret these models. So I'll start with the very first one that we published in 2019. It's called a summit. So they're one of the very first approaches that can scalably summarize and also interactively visualize what these networks have learned. So you probably have heard of it a lot. Like whenever people talk about deep learning, they say, oh yeah, deep learning is kind of like mimicking the brain, although in practice it's not really that similar. So what it's really learning is like these features. So for example, you have images of wolf and you wanted to do a classification, well, then what we think the model has learned, or the neural network has learned, is it's probably trying to detect if they're legs, if they're like fur, if they're like pointy ear, and well, if they have all these, then together, so now we can give the final outcome of like a wolf. Right. So that is what people have long been saying that should be the case, but no one really able to show that or to visualize it, looking at the connection, looking at the related concept. So Summit, we developed it as one of the very first tools that can enable us to visualize that. So Summit is a web-based tool. You can actually go play with it. The link will show up shortly. You can go play with it. And then here I'm showing you a quick demo of how Summit works. So on the right-hand side, that is we call the graph summary. So in previous slide, you see that pictorial illustration. That is what we want to be able to tell, right? This kind of network node link diagram. So in our summit system, so on the right-hand side, that is the graph summary. And in this demo, what we're showing is that we're going to pick a class out of the ImageNet data set. So ImageNet has 1.2 million images and 1,000 classes. So here we're picking the class called Tench. So Tench is yellowfish. So I picked that on the left-hand side, and you'll see that Tench class classification is 92.1 accuracy, so pretty good. So our model, in this case, Inception V1 model, doing 92% accuracy. So that's really pretty good. So now we can look at what is the model, what does the model has it really learned, right? So that's on the right-hand side. So our technique already summarized it, picking out the most important neurons and edges out of it. And we look at some lower layers, so further lower down, the earlier layer, further towards the top, the later layer that's closer to the prediction. So we look at the earlier layers. Here, each square is one neuron that we determined as important. So there's a lot more detail in the paper about how we do that. But here is one of the neurons in mixed 4B layer. You mouse over the neurons, and you will see a pop-up. Here we show actual data example. So these little squares actually snippet from the actual ImageNet data set. So what that means is that these kind of little forehead and eyes are actually activating this particular neuron 405 in mixed 4B. And if I look at the neuron, yes, go ahead.
If this is finding some of the most useful convolutions, then that implies a rank order. Could that also be to find the least used convolutions as good candidates for pruning? Like if you wanted to speed up scoring.
Yes,
and then is that something that you could export?
Yes, great question. So yes, so short answer is yes. You can do a rank order. In this case, we're picking the one that has the strongest activation, but you can certainly modify it to pick out the least important and then try and prune that. Yeah.
And the activation, is that based on the distribution of your training or test set, or is that based on just something inherent from the network architecture outside of the data set?
Right, it's based on the data, the training data. Yeah, so great question. Yeah, so it's based on what get activated the most. Yeah, but you can have variation for that too. You don't need to always do. So what we present is one of the, we start with the simplest way. So that just see, okay, does it work? Okay, it works. Okay, good. So now we can probably do other things. Yeah. Thank you.
Is it by the activation that's near zero or has a least variance? Like if a given convolution always outputs 0.1, but it never varies, then that could be one indication of unimportant because it just doesn't vary regardless of the input. Versus being an output of always zero.
Yeah, so it's quite a bit more details in it. So at the high level, it is based on the activation. So for example, for one neuron, we want to say, is it important or not? Is actually we pass through all the hundreds of images through it, and then based on the activation distribution, and then we try to keep the top ones. So yeah, so that's even more details than what I just described, but that's the main idea. Yeah.
Thank you.
Yeah, you're welcome. So okay, so let's continue with the example. So we just look at was some of the neurons and the lower layer. So I think that should already surprise you a little bit because here we're dealing with the tench class, yellowfish. However, what we see actually these people class. It's not only until a little bit later that we start to see some fish, right? So that should raise some alarm. Particularly this is for classifying fish, right? So if this is doing in person presentation, I'll do as a pop quiz and then say, okay, so why are we seeing so many people? Right, so this is a link, you can go play with it. So yeah, so that would be a pop quiz and so why is it? So why do we see all these human eyes and heads and so on, but not fish? So I hope there's some people like fishing in the audience. Then for those you are, then you would know that tench is kind of fish that people like to catch and take picture of. So what that means is in the ImageNet data set for this tench class, majority of the images in that class were actually people holding the fish. So what that means is here, tench class 92% accuracy, but is actually using a lot of human or the people features to help with the classification of tench. So then now that raises the question, would you feel comfortable using this model that seemingly have really high accuracy in classifying tench for your practical usage? The answer may be yes, or maybe no. So if the data that you're handling, the images you're handling are really people catching, who are holding the fish, then probably yes. On the other hand, if you're mainly dealing with images really close up of the fish, like no people, then probably you'll be doing pretty poorly at the classification. So so that got us thinking a lot about like, okay, so wow. So originally we just wanted to use Summit to kind of think about like how useful that might be but then it seems like we're going to do we should do a little bit more than that. And that actually motivated us to build a follow-up system called Bluff. And that's exactly to solve the problem. So we use the same idea as a summit, like a graph representation. This is also a tool you can try, by the way. But instead, now we're focusing on, can we understand what an attack, if you have an attack, I think an image classifier, what an attack is really exploiting in making the attack successful. So here I'm showing you a screenshot, very similar. We just saw Summit, and particularly here we allow the user pick not only one class, not like Tench, but we actually allow them to pick two classes. So the first class is what is the benign one. So here at the top you will see understand how neural networks misclassify giant panda into armadillo when attacked. So that means the benign class is giant panda. So that means you have these giant panda images. And the armadillo is what you want the target, the manipulation target to be. So again, you can actually want to turn it into anything. But here we pick armadillo. So now in the graph summary, what we show now is we separate the neurons. So we label the neuron in different ways. So which neurons are only activated, only important for the giant panda class, which one are only important for armadillo, which one important for both, and which ones are exploited by the attack. So that means it only get activated because of the attack. So in this case, since we're trying to change the classification from giant panda to armadillo, so we see that, oh, actually some of the neurons responsible for, in this case, the scales, the bumps, the mesh, that are features that you expect in armadillo, but are not present in giant panda. So those get service or get activated because of the manipulation, pixel manipulation. So now for the first time using Bluff, you can see, oh, okay, so now we know why are these attacks successful, because now you are really boosting some of these neurons, making them activate while they actually should not. And that gives rise to the final incorrect or the manipulated outcome of armadillo. And so we try to generalize this idea to beyond. Actually, I want to see if the top is covered. Oh, hopefully it doesn't cover. Yes. So we try to generalize this idea of understanding attack to beyond image classifier. As I mentioned, the image classifier is probably something that people would first start to look at because that's probably has been studied the most, and also in practice is probably used the most. So we extended our investigation to some of the latest techniques like human action recognition, for example. We just published as a demo recently at Triple AI 2021, a system called Skeleton Bits. So similar motivation as Bluff, also to help the user understand what these attacks are doing. So particularly here, we are showing how the attack, in this case, we're running PGD, projected gradient descent, to try to manipulate a human action recognition system. So here, the action recognition is based on the human skeleton. So in green here is the benign skeleton. So we're doing lunges. So a video of people doing lunges, and we want to say, okay, so can we correctly classify, recognize this as lunge action? So in green, so that is the benign skeleton, and then in orange, that is the manipulated skeleton. So that means the attack changed the skeleton. In this case, pretty obvious to human beings. It's distorted in ways that humanly impossible. Sometimes it's even teleportation. And while for benign, you expect it to be standing upright. Right. So here you can look at the comparison, how they are different. So they allow us to dig a little bit deeper into how the attack works. So this is a work in progress, so there's a lot more work to do. But now you can really localize temporally, spatially, down to individual frames, what is getting manipulated for human action recognition. So again, there has been work, particularly from the machine learning area, computer vision area, where they say, oh, we can attack your action recognition system so that it can mislabel. But for a long time, they are not able to answer. So what the manipulation is really doing, is it manipulating all frames, or manipulating some frames, or like how is the manipulation happening? So now we can actually visualize, okay, so it's actually not all frames. You don't need to do it for all frames. You only need to do some frames. And for some frames, you can do it like really out of whack, and then that's it. That can then do the manipulation. That gives us a lot of idea about how do we do the defense, because now let's say, well, if we're really dealing with this attack, then one way is maybe we're going to impose some temporal continuity, spatial continuity. Again, this, but the human being we take for granted, right? Because we don't expect people's skeleton to twist like that, right? But then for the human action recognition, it doesn't matter. So then all they see is, okay, key points, all these human key points. Okay, does it make sense? Does it match? It doesn't match. Okay, another classification. So that gives us ideas about, oh, maybe we can impose some temporal continuity or a coherence both in the spatial and temporal area. So this is still work in progress. So hope I can share more of the result later, very soon. So we're working on with these models. It could be like human action recognition, it could be image classifier, deep neural network. One thing that become pretty apparent is that not only novices help, not only people who are new to these things help, it turned out even experts need help. So this is joint work, GangLab is joint work that we did with Google Brain. And that was motivated by observation that experts need help, and particularly in the context of deep generative models, or again, generative adversarial network, where now you probably have heard of it a lot, right? So this is one of the foundational methods that enable techniques like deepfake, for example, generate things that look really realistic, but that is actually fake. Right. So with Google Brain at that time, we were trying to say, oh, so can we help experts better train or fine tune, understand these models? Because again, if you ever work with it, it's actually not that easy to train. So it's pretty tricky. So originally, we was okay, so maybe we should build a tool to help the expert to understand, interpret this model. So you may ask, why is it hard? Why we focus on it? So the reason is that again, it uses two competing neural network internally. So using an everyday example, you can think of these two neural network. One is being the we call it counterfeiter. The internal we call it generator, and then the other one, discriminator, we call it police. So the everyday analogy could be that the counterfeiter tried to make fake bills, and so bills that look real, and the police is the one who would try to catch these fake bills. And what we would expect, like initially, maybe the counterfeiter is not that good. Right, generate some fake bills that doesn't look very good. And police, of course, have access to the real bill, so that the police can tell really quickly, okay, so, well, no way, this is a real thing. And of course, counterfeiter, if they don't get caught, or they get released, well, they will try again. So now they make the bill even more realistic. And while for the police, also as they see more sophisticated fake bills, then they also improve, right? Because now it's a harder task for them. So what that means is that these kind of go back and forth. So counterfeiter continue to improve, and eventually they make such a fake bill that's so real that the police have a problem telling them apart. Right? So what that means is now the counterfeiter can output this fake but realistic looking data as the output of the whole gang model, and then the training is done. And so that's all the everyday example. Of course, in practice, counterfeiter, we call it generator, police, we call it discriminator. So a question is, how do we show this? How do we explain this kind of overview or the inner working of it? We actually tried quite a lot. So originally we tried, maybe we just have a whole bunch of visualization and some sliders that people can change. Each one of these is neural network. Can we change the slider neural network, and then hopefully they will understand. But it turned out it's not really that easy to understand. So in the end, what we do is we actually use the analogy. We take advantage of analogies because it's easy for people to understand. But now we just use the same spatial layout, but we put it into the interface of GangLab. So again, this is something you can try right away. In your browser, you don't need to install anything. Actually run using your GPU or CPU locally. Showing the demo down here below. you see the two big boxes. So on the left-hand side, so that's exactly the generator or the counterfeiter. You'll see that the data, in this case, the grid, that's showing you how the transformation of the data is happening as the counterfeiter or the generator improves over time. And then on the square, big square on the right-hand side, so that's showing the discriminator, the police, by trying to look at the decision boundary. And on the right-hand side, the biggest model you can see that is to see how the fake data, the purple dot, is incrementally become more and more similar to the benign or the correct data, which is the green dot here. So this is a very interesting way, and also a very new way, exciting way to help people understand what is it doing. And in this interface, you can, if you go to the website, you can actually change the setting while the model is training. You can change the number of neurons, number of layers, and the generator and the discriminator. You can change the learning rate and all those. So when I released it, so it got a lot of attention. So this is one of the very first time that people can actually do all these GAN training interactively and also visualize the result directly in the browser without installing anything. So a lot of likes, a lot of retweets, and now it's also used in like classes around the world because this is a very easy way for students to learn about it.
How would you use this for something more complex, like a truck versus a crane? You know, like the lower part of the truck and the might look like a crane with wheels. You know, as opposed to just a simple circle.
Yes, you can actually try. You can draw your own data. So circle, this is one we draw, but you can also draw other ones. So yes, so go play with it. I encourage you. Actually, after developing GANLab, GANLab is a more advanced technique, and that actually got us thinking back a little bit. Well, so if the GAN approach works well, would it also work for other models? I think particularly for, let's say, models that may be beginners or new students, students who are interested in machine learning, deep learning, but they may not be sure like whether they want to learn about it, because practically currently there's still quite a bit of hurdle for students to really learn about deep learning. Often they need to take a lot of prerequisite classes before they even play with some deep neural network models. So we think, well, maybe we can use the same approach as in GANLab. That's exactly what we did. We built the CNN explainer, a model. In this case, the CNN is probably one of the very first things that students will learn when take a deep learning class. And in particular, in this case, we built this, again, same tool, web-based tool, using similar architecture, where we allow the students just go there. They don't need to install anything. They can pick one of the data example up there. Here we're picking a coffee, and then we can see how the coffee image get classified through the whole network, from the left-hand side, which is the input, going through all the layers in the CNN. And more importantly, is the users can click on the individual layers and then look at how the math is done. So that has been a big gap in current learning. And actually, this is work that we developed with both students and also instructor. That's a big gap that the experience is. The current way of learning CNN is often that they will learn the math kind of in isolation, with the CNN. And then they need to kind of remember like how all these things fit together. And here CNN fill that gap. They said, well, so maybe we can just connect all of them and give you an overview. You can drill down, and we visually show, if it's a convolution, what does it mean really doing? Here you can even play with it, move it around. You can change some of the settings yourself, and so connecting everything. So again, when we release it, I think we have filling a very critical gap in the existing space. So that also got a lot of attention, and now also using a lot of classes around the world. So we think this is a really exciting, I think, a way particularly to broaden access to these technologies. So because you remove a lot of barrier of entry now, so you don't need to install anything. Even students who are new, maybe even like high school, middle school, they just want to know, oh wow, okay, so there's like these deep learning techniques that are now used. Like, what is it all about? You don't need to say let's take 10 classes first. You can just go and play with it. So I expect to continue to build a lot more tools that following this similar strategies, so that we can broaden access. So I'm going to wrap up actually with this final slide. So I've already given you quite a few examples of the latest work we do, particularly in the space of interpretable AI. There's a lot more that we haven't talked about. There are also the other examples from my group. So I'd like to end by pointing you to surveys. And I like those surveys a lot. So on the left-hand side is a more recent one. This is a comparative survey summarizing the human AI interaction guidelines from some of the big companies, particularly Microsoft, Google, and Apple. So you may have seen this. Actually, I think Microsoft is the first one that came out. So basically, you say, hey, if you want to develop AI system that interface with human being, here's some guidelines. So of course, once Microsoft released it, then Google also released that version. Apple released their own version. So we were curious to know, so how do these guidelines differ? Right? So what is more important to one company, perhaps, or they pay more emphasis than the other? It will turn out to be, well, there's some overlap, but there's also significant differences. So I highly recommend giving this a pretty short, interesting paper to summarize the human AI interaction guidelines. And on the right-hand side, that is also one of the latest survey that from our group looking at the visual analytics in deep learning space. So that means looking at some of the state-of-the-art visualization techniques that help people understand deep learning. So it's a pretty recent research focus. So here we are doing all the work for you. Basically, we summarize over 50 papers using the 5WNH model. So why is a technique developed? Like what for? Like when is it doing the interpretation? Is it like doing training, after training? For whom? For example, is it for novices, for machine learning developers? And how do we do that? Do they do a graph-based approach? Do they do like heat maps and so on? So we summarize all these down. So highly recommend these if you're interested in learning more about visual analytics in deep learning. So I'm going to thank you all today for attending and for listening. Yeah, thank you.
Would you be willing to post on the meetup site or on the chat link to your slides? Many times people ask about slides.
Yes, definitely. I will do that. So okay if I share that after the talk?
Okay.
Yeah.
And then do you know about research on adversarial recognition attacks that work on animals?
On animal? Oh yeah, I think recently I saw one. I forgot from which group, but yes. Yes, so the yeah, I think that particular ones, I forgot the, not off the top of my head, it's pretty recent, like within the last few months. Yeah.
Okay. And okay. And then as far as people that, is there works on defense on face recognition? Like I think CMU had some work on eyeglasses that people would wear that were kind of flat and bright colored around their eyes, but just as ways of defending if they didn't want to be recognized. Any comments on that? Or
yeah,
other kinds of ways where people didn't want to be recognized by, as far as their faces to name them, their identity?
Short answer is yes. I think it may even be a majority colleague, Salvador Das. I need to look at outside of his name. GT colleague. I need to check with him. Yeah, so there's work like along the line of kind of privacy, right? Because now that a lot of people's images are on the web, whether they like it or not. So sometimes people say, "Oh, can I actually have images that I intentionally try to fool maybe in a good way? In this case, I don't want to be detected by these." So yes, I remember there's some recent work on that. Yeah.
Oh, okay. Okay. Any other questions from the audience or ACM Council? Okay. So I didn't have other questions then. So thank you so much for being a speaker tonight. And then just for the general audience, we made a recording of this for tonight and we'll post it up on YouTube. I would assume within a few days to a week, we should have it posted on the YouTube based on past experiences. Okay, well, thank you so much. It's been great having you as a speaker. And we'll post a link to the speaker talk on YouTube. But in general, if you look at YouTube and you search for SF Bay ACM, then you'll find our full channel. And also, then our recent postings will be at the top of that channel. Any other comments or announcements from the ACM Council?
I wanted to mention a recent talk we had on AI trust, adversarial attacks.
Oh, okay, sounds good. And then there was various links mentioned during this talk, so I'll post those into the discussion section of the meetup for this particular talk. And then if the speaker could post a link to their PDF of their slides, that would be great. So thank you very much, and appreciate you giving the presentation tonight to the San Francisco Bay Area ACM.
Thank you for having me. Yeah, thank you.
Okay, thank you.
Okay. Good night.
And thank you, students and broader community as well.
Thank you. Thank you.
Bye.
Bye. Bye.